Hello and good morning, everyone. I'm Laura Betts, and I am honored to be hosting today's StoryLab. This is hosted by NASA's Goddard Space Flight Center, and today we are going to be hearing from Dr. John Mather, and he is one of NASA's most engaging and prestigious team members and has won the Nobel Prize. So Dr. Mather has many great accomplishments, among those the Nobel Prize he won with George Smoot for his work on the Cosmic Background Explorer COBE project that helped measure heat radiation from the Big Bang. John is not only that, but he's an exceptionally generous person who donated all of his prize money to the education of students. I'm so lucky to work with John as a part of NASA's James Webb Space Telescope project, where he works as the senior project scientist. Launching this year. On top of all of that, Dr. John Mather is an exceptional storyteller, and we are so lucky to be hearing from him today. John?
Well, thank you. Thank you, Laura. I'm glad people like the way I tell my story. So I thought to talk with you today about storytelling is a little funny instead of telling stories themselves. But at any rate, I thought let's talk about what it's like to share the Nobel story. So just a few thoughts about what I try to do in my talks. So let's see if I can do this, talking about talking. So my perspective is it's always about the audience. And so you have to figure out who that audience is. And one example of why that's important is when I went to Stockholm to give my talks about the work on the COBE project, I looked at the audience and I saw this audience is from the general public. This is not my professional colleagues working on the details of cosmic microwave background radiation. This is interested public. We're not going to give them a very highly technical talk with all of the details. We're going to give them a interested public kind of talk and tell them stories about this rather than what some of the other Nobelists did, which they gave talks that I could not understand, and I wondered why they did it. So that's pretty important. Who was the audience about? I took media training here at Goddard, and one of the most important things that they told us was everybody's always listening to this radio station, WIIFM. So what is that? It's what is in it for me? What's in it for me? So, okay, that's essential. So people are always listening with that in mind and not necessarily with it's really cool that you're here. It's what's in it, what's my next opportunity, what do I get to do about this? So other things people have told us is that stories are much more memorable than facts. So tell people how you found out, who you are, don't just say this is it. I thought also people have been much more interested than I ever expected in who am I. So for me, the story of the COBE project is always working with a team. There were 1,500 people that worked on the COBE mission. And so whenever people introduce me and say what a great guy he is and all this, I say, by the way, it took a team of an immense number of people. And this is not because of me, this is because of us. So coming back from NASA headquarters after we got the Nobel announcement and a press conference, I came back to Goddard and I was greeted by an entire auditorium full of people, and I'm at the back and everybody is there waiting for me because I'm a little bit late. So I pulled my badge off my chest and I hold it up to over my head and I walk to the front and I'm saying, I'm part of this family. So it still gives me goosebumps to remember that emotional feeling that I had, and I think people shared it, to know that we had done something together. So that's part of how I tell a story. I like to tell a little bit of history because that's what got me interested in the science to begin with. So let me see if I can work this screen thingy here. So what I'm going to offer you today is an excerpt from a talk that I did for the Maniac series of lectures at Goddard. Did them over in building 33. And quite a few have been done over there. They're organized by Charles Getebe a long time ago, and I'm not sure who's still doing it. But at any rate, people tell their life story. And it's if you want to see how people do that, there are many wonderful talks over there. So here's the link on this page. You can see where this one is to watch it yourself if you want the long one. Or if you just look up Goddard Maniac Talk on the internet, it should turn up this whole series. So anyway, that's what I have in mind to do, just to give you an example of what I do, and then we can talk about it later. So I'm interested in astronomy, but I'm also interested in history. So how did we get to today? Well, Archimedes, great mathematician, worked for the Defense Department of his day in Syracuse in Sicily. And I've actually been to that town now, and I've walked on the ground there, and I thought, I probably walked on the same pavement stones that he walked on. I don't think I absorbed anything from him that way, but over 2,000 years ago, mathematicians and scientists were already working for their Defense Department. Then skipping forward a couple of thousand years almost, thinking about the internet revolution of 1450, when Gutenberg made a printing press and started upsetting everybody. Because when people could suddenly read the Bible, they said, actually, that's not in agreement with what people have been teaching us in school, in church. So let's have a revolution. We're going to have a new set of religions. So it was extremely disruptive back then. As it happened, it came just before Copernicus was working on his ideas about the solar system, and also just about a century before Tycho Brahe, a great Danish astronomer, was working on observing the motions of the stars and the planets. I think that's the last and only time that an astronomer was receiving 1% of the gross domestic product of a country. So he was working that way, and he produced the observations that Kepler needed to conclude the story of the elliptical orbits of planets. I put in Galileo here. He was one of my heroes even as a child. And he was working for the Defense Department of the day. When he knew how to make telescopes, everybody wanted to buy them. And it was of tremendous military importance. So one can tell this story even up into modern times if you want, because now there's a book that tells this story, and I can't recall its title right away. Anyway, Kepler, Newton, Darwin. Darwin was another one of my childhood heroes because he was challenged to existing authority. So I grew up knowing that science was really important. It was a little dangerous because you could get in trouble for discovering things. But that just meant to me that it was more important. So keep on doing it. So a little more history. Here's Albert Michelson, first American Nobel Prize winner in physics. He's very famous for inventing the technology that I used for the mission I call the Michelson interferometer. But in his day, he apparently thought that the great hints about new science would be coming from more decimal places. So it's later other people have denied that he actually said this, but in about 1900, people thought we found everything. And that was just before Einstein interpreted Michelson's measurements to say, well, there should be relativity. So we have been surprised all of the time. That's one of the great, wonderful features of being a scientist. It's surprises all the time. So I talk a little bit about my family. My mother was a first grade teacher. Her father was a bacteriologist, helped develop penicillin production, indirectly responsible for saving the life of Che Guevara, who needed penicillin. You never know what effects people will have. My family's name comes from England. My dad was a scientist, and his father was a missionary. So there's an amazing set of stories there. My wife is a ballet teacher. So that's one of the reasons some of that prize money actually went to support ballet students as well as science students. So anyway, heroes, they enable me to dream big, having a hero. So more heroes. Well, here on the left is Schrödinger, who's told us about how particles are waves and waves are particles, quantum mechanics in 1925. Can you imagine? It's almost a century that we've had that information, and it's still mysterious. Here's Robert Goddard, the first person to fly a liquid-fueled rocket. And history says from the New York Times, this cannot work. New York Times declared the rocket could not work, but of course it did. So we have named Goddard Space Flight Center after him for his pioneering work. What else happened in 1927? I'm showing here Albert Einstein with Georges Lemaitre. Georges Lemaitre was a priest, a Belgian priest, and also a great scholar. Had his degrees from MIT in physics, and he understood the measurements that had been made, and also understood that the Big Bang could be a real idea. He called it the primeval atom. So he explained this in print. Einstein did not agree with it. He said that's wrong, that's a terrible mistake. But in actuality, Einstein was wrong. He has been wrong a few times. So, by the way, Lemaitre also got to meet the Pope, who was his boss, and the Pope wanted to know, doesn't your story confirm what it says in the Bible? And Georges Lemaitre said, well, that's not what we should use it for. Science is science, and it's not about God. Interesting. So here is Edwin Hubble at the focus of the great telescope in California called the Hooker telescope that he used to make a chart. And this chart is the chart that shows the universe is expanding. So in 1929, he convinced people from this chart that distant galaxies are going away from us with a speed proportional to distance. And this was the first time that we ever had the ability to measure the age of the universe. So if you divide the distance of a galaxy by the speed of motion, you should get the age of the universe. That's what the chart gives us. And of course, he was wrong. The answer he got was 2 billion years because his distance scale was incorrect. But anyway, we found out later the idea that the universe is expanding was correct. We call it the Big Bang story, but that's actually very misleading too. So here are some more people that were my heroes, or I didn't know them all at the time. This is Lyman Spitzer, a great astronomer who at the end of World War II was working with the Defense Department and the RAND Corporation, and he wrote a report saying, well, you know, we should be able to build telescopes in space. It would be much better than having them on the ground. Let's do it. So he wrote about that, and we didn't do it right away, but it did take a little while later we were able to do it. Here's Sir Fred Hoyle, a great cosmologist, who is the one that gave the name Big Bang to the expanding universe. We remember him for that, partly because he has confused every single person with the name ever since. The Big Bang sounds like it's a firecracker going off somewhere, but it isn't. And so one of my missions in public talks is to try to convey a more correct impression about the expanding universe. Something else happened in 1946. I turned up. So people always giggle when I show you this picture, but yes, indeed, real people start out small. And you never know what the next generation of small people is going to do either. So what happened then? Well, in 1948, a couple of years after that, these people, Alpha and Herman with George Gamow in the background, were thinking about the Big Bang. And they said, we should be able to calculate something about it, tell you how hot it was. We understand the properties of neutrons now, after we learned about them to do nuclear physics in the nuclear weapons business. So, okay, let's calculate. They said the universe should have a temperature of energy left over from the Big Bang, and they gave us about the right number, about 5 degrees Kelvin, and then nobody went to look. So nothing much happened, even though 300 people came to watch the thesis defense of Alpha here down in town at George Washington University. It was a very big deal at the time. Then nobody did anything. So let's see, what have I got next on my chart here? Oh, in 1954, Mars was coming very close to us, and my parents took me down to the Museum of Natural History in New York. We heard all about the canals on Mars. And gee, wouldn't it be nice if we could see them and go there and learn about the civilization of the living creatures that had made these canals. Well, actually, we couldn't see them very well in 1954. And now we know the reason we couldn't see them is they weren't there. We do know, I think, where they came from. These are maps of the blood vessels in the eye of the observer. And he was fooled into thinking that was something real. 1954, very disappointing, we still haven't found those canals. Or the little green women. People say little green men, they should say little green women. At any rate, 1957, this country got a complete shock, even though we had been warned many times, that the Soviet Union flew a satellite called Sputnik, and it scared the bejesus out of this general public and caused the United States to be able to enter the space age too. So we had been already working for quite a few years to develop rockets in support of the International Geophysical Union, but they had not yet worked. Anyway, so suddenly this country said, uh-oh, we're scared to death. Better get some science money out for those kids in school because they're going to support us and prevent us from being taken over by the Soviet Union. So it was kind of scary in those days. We were taught in elementary school that in case of nuclear attack, we should hide under the desk. Well, it doesn't take very much smarts to figure out that that's not going to work. But people did understand, well, better get something more. So suddenly there were science fairs for me to put my science interest into, and there was public programs for me to apply to. So I got to have lots of activity because of that scare. And the country decided to support science and engineering again. Of course, we had done it very well during World War II, but then we sort of backed off because, well, we won. So anyway, time passed. So what happened for me? Well, I went to elementary school in rural New Jersey. I went to public high school in rural New Jersey. But then I did have the opportunity, because of the giant scare from the Soviet Union, to go off to summer school while I was in high school. And I studied math and physics. I thought, this is absolutely the most important and exciting thing I could possibly be working on for the rest of my life. I still think so. So just to give some hint of, you never know what's going to happen. This was a better public school than I appreciated at the time, because they gave me a good shot at going forward. So where did I go? Oh, this is where I lived, by the way. This is the Rutgers University Experiment Station. And this is the view from the front yard of my house. So that barn there, that looks like a barn, was actually a barn for keeping bulls in. It was also connected to a research laboratory with microscopes and chemical things, and liquid nitrogen. So I was beginning to get an education. Even here in this very rural place. So this is where I lived. There's a view of my house way up there at the top right. That's the house I lived in. There's the map of New Jersey in the top left. I rode to school in a school bus like that. And in the lower right corner is a picture of Newton, New Jersey, the public square. So sort of as it was more or less 100 years ago, hasn't changed very much. A slow-moving area then. Now it's changed. And it turned out to be a good place to go to public high school. So what's then after that? Well, 1958, NASA was created. So here's the document from the 85th Congress, I guess, of the United States, saying, let's make NASA. We've got to beat the Soviet Union, And this is the only federal science agency which says in the charter, please tell the public what you're doing. Please fund public outreach. So Laura, I see you nodding there. This is the document that says we should do what we do. Other science agencies need this, but they don't have it. So 1958, now shortly after that, 1962, here's Jack Kennedy. I'm not going to play you his story, but this is him announcing that we're going to go to the moon before the end of the decade. So we did it. Now, these days, we can't even have a discussion before the end of the decade, but he said we're going to go. And the man who made it possible is, let me see, there he is, James Webb. James E. Webb was the second administrator of NASA, and he was the man who went to Jack Kennedy with a plan, and he made it happen. And also he said, Mr. Kennedy, we should be doing this not just for science, not just for public presence for the military demonstration that we can fight a war without fighting a war. We need to have some science that we can keep. So can we please open up some space science laboratories at universities around the country? Oh, Kennedy said no, but after a while Kennedy said yes. So we have that. So not only did James Webb start the Apollo program with Kennedy's backing, and he got it right. Here's an interesting story. James Webb, on the way to see the president with the proposal, said, I don't think I've got enough money in my request. I better double the budget request. So he did, and it was enough. And if you can try to imagine what it would have been like if he had not done that, it would have been the world's most terrible disaster that the United States said they would do something and then they wouldn't, then they couldn't. So he was smart enough to ask for what it really took. And one of the parts of that is he knew that he shouldn't believe people like me who were too optimistic. You know that. Scientists and engineers, we can do stuff, but he was the manager. He said, you better prove it. So, okay, more steps along the way. Here's the college I went to school in. Some pictures of this college. Picture of Nancy Roman, who was one of the very first people to get a PhD in astronomy as being a female, and she became the first head astronomer at NASA headquarters. Another famous astronomer from that college is Sandy Faber. At any rate, now we've named a telescope that will be launched into space after Nancy Roman. So what happens then? Well, here is 1965. These are the people that discovered the cosmic microwave background radiation. I told you that nobody went to look in 1948 when it was predicted. By the time 1965 came around, most people had forgotten. And these people had built a radio telescope, and they didn't know that they were going to find something. They were doing this for Bell Labs, and they were astronomers and trying to do some communications work. So they pointed their antenna at the sky, and it came back with extra noise in it, and nobody knew what it was. Meanwhile, just down the road in Princeton, there was a group that was looking for that cosmic radiation, but they hadn't finished the equipment yet. Anyway, so these two got their Nobel Prize for discovering the cosmic microwave background radiation, and that became my life by a very roundabout method. So I went to graduate school in Berkeley, finished up my college career and went off to Berkeley. What I really wanted to do there was to become a theoretical physicist, just like Richard Feynman. But I asked around, can I do this? And they said, no, are you independently wealthy? Because there are no jobs for people like that. So I found a project to work on measuring the cosmic microwave background radiation, which was a new thing. And so I started in working on it, and sure enough, it got interesting. So physics was very different back then. Just to this is like proving that I walked to school uphill in the snow, both directions, barefoot. But this is actually what things were like in the old days. We made things with vacuum tubes. Transistors had been invented, but they were not everywhere yet. The pocket calculator did not yet exist. and a rather advanced laboratory computer was programmed with paper tape. So I can't believe that people made as much progress as they did, but they did. So here are the people. There I am in the lower left corner with lots of hair. And there's my thesis advisor and my fellow investigator, Mike Werner, who became my counterpart on the Spitzer Space Telescope, by the way. So people, 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 that's my story all of the time. I would be nothing without the other people in my life. So here's the apparatus that we built first. It took it up to the mountaintop. It worked, and we didn't find out anything interesting. So that's boring. Then my thesis advisor invented this new idea. Let's take a balloon payload and send up a spectrometer suspended from a balloon 25 kilometers above the surface of the Earth. And that was my real thesis project, but you know what? It did not work. So here I am. I've done a lot of time. This is a really hard job. So Paul said, okay, you can write up a thesis about a project that worked but didn't do much, and another project that will work sometime but hasn't yet. So, okay, I got my thesis, I got out of school, and I got a job at NASA Goddard Institute for Space Studies in New York City. And so that's where I went next. So there is the laboratory. It's right upstairs from Tom's Restaurant. So some of you know from the Seinfeld TV series about Tom's Restaurant. There is a real one, and that was it. And I ate there every day. I lived in a shared apartment, and there's a supercomputer shown in the right-hand corner down here of the computer like the one that we had at the Goddard Institute. Okay, so I was there, and NASA said, we want proposals for new satellite missions. I said, see, my boss, my thesis project failed. We should try it in outer space. So he said, okay, we'll send out, we'll call up our friends and we'll write a proposal. And we did. And that was sent in. And here's actually a little more about that process. We didn't know that there were going to be 150 competitors. NASA did not know that either. They thought they might get a few. So this was just after 5 years after we landed on the moon for the first time. And NASA was wondering, what are we going to do now for science? It turned out that not only our proposal was on this topic, but there were two others from Jet Propulsion Lab and from Berkeley. So what are we going to do? Well, NASA actually decided a little while later that, yes, we're going to do something. And they made a team and said, come down to work at Goddard Space Flight Center. We're going to assign professional engineers to work with you. And so in those days, this was the concept. And the team that they assigned to us was just finishing up the International Ultraviolet Explorer, the IUE Observatory, which was operated from the basement of Building 21. You could go there if you had observing time on that telescope and sit there and drive the telescope. It's not something we do anymore, but it worked well then. Anyway, here's the sketch that I drew that was in our proposal for the flight apparatus for the Cosmic Background Explorer. So it didn't turn out exactly that way. Here's sort of words to explain the history. The short version of it is all kinds of stuff happened to us. The biggest one was the Challenger blew up. And we thought this COBE satellite was going to be launched on a space shuttle from California. And so, okay, well, that's not going to happen. So we had to redesign the whole physical structure of the Cosmic Background Explorer satellite. And suddenly we went from being sort of lowest on the totem pole to being top priority, because NASA realized if we could do what we said we could do, we would be the first science mission after the Challenger. So it turned out to be correct. We were. We went up a few months before the Hubble satellite went up even. So suddenly we went from being a small in-house project at Goddard, which was not drawing much of attention, to top priority. Everybody's got to get this to work right now. And so we did. And so we launched it in November 18th of 1989. And right away we started getting some observations. I like to show pictures of the people. So these are some of the people that were part of our initial team. The people with their underlines under their names are the team members, and these are photographs taken at various times. Anyway, Ray Weiss, by the way, in the lower left corner, got his own Nobel Prize for measuring the detection of gravitational waves from merging black holes and merging neutron stars. So he was working on 2 Nobel Prize projects at the same time. So here's what the satellite looked like in space. There it is. Of course, it is not exactly the same as that sketch that I drew, but it's awfully similar. So this is got 2 instruments in the inside up in the top that are cooled by liquid helium to 1.5 degrees above absolute zero, as well as 3 microwave receiver boxes. And so that was what we used to earn a Nobel Prize. So where was it built? It was built at Goddard Space Flight Center. The only big piece that was not built there was this helium cryostat in the middle, which was built at Ball Aerospace. This was such a huge project inside Goddard that afterwards we said, well, it sure feels good when we stopped. This was too hard for us. Because we ended up needing a large fraction of the engineering directorate's resources. Nevertheless, we were very proud that it worked. Here's a sketch of how the spectrometer worked. I don't think I'm going to go into detail here because it's not about that today. Here's the first data that we got. We got a standing ovation for showing this to the Astronomical Society about 6 weeks after launch. The theoretical prediction of the spectrum of the microwave radiation is here. It's the smooth curve, and you can see all the little boxes are right on the smooth curve. So basically, this was the observation that says, yeah, the Big Bang is about right. Nothing very complicated or surprising happened after the Big Bang. And there was no conversion of energy from any other sort. There was not decay of primordial particles. No cosmic strings. Our theoretical colleagues are extremely ingenious at imagining things that might have happened, but they didn't happen. So suddenly this theory of the expanding universe, which was a bit shaky before this, was the only surviving theory. Another story about that, when we showed this chart to the Astronomical Society, the person chairing the session was one of the people who thought this couldn't possibly be right. And he said afterwards, they've swallowed it hook, line, and sinker. So, okay, I guess we did a good job because it was the right answer, I think. So Ellie Dweck is a cartoonist as well as a scientist, and he's on our team. He illustrated this with, gee, it's awfully cold out there. The temperature of this cosmic microwave background radiation is 3 Kelvin. So here's another sketch of how the how the microwave receivers work to make maps of the sky. I'll skip over it to say that this is the result of the second instrument, microwave receivers, to make a map of the sky, showing whether the cosmic heat is the same brightness in every direction. And as you know, when Stephen Hawking saw this chart, he said that was the most important scientific discovery of the century, if not of all time. And it took us a long time to fully appreciate why that was so important. But sure enough, these spots would not be here if the Big Bang was not the right story. And they wouldn't be there, well, we wouldn't be there if the spots weren't there. So the story is gravitation acting on the hot and cold spots, which really are density variations, was able to stop the expansion of the cosmic material and turn it around and make galaxies out of that primordial stuff. So we're here because of that. A lot of them, most of those spots come from cosmic dark matter, which astronomers can deduce, but we can't see either. And eventually, if we understand quantum gravity, we should be able to predict why those spots are there. But at any rate, right now, we just know that they are there, and we're here because of them. So what did the Nobel Prize happen? Well, in 2006, one morning I was waking up. I knew it was the day that a prize might be announced, so I'm very interested. Someone had tipped me off to think that maybe I should be interested that day. Got the phone call at about 5:45 in the morning, which corresponds to just before noon in Stockholm, that we've been chosen for this great prize. And these are the words: for the discovery of the black body form. So that's that curve that I showed you with the little boxes on it. And the anisotropy. Anisotropy means an means not, iso means the same, tropy direction, so not in the same in every direction. The cosmic microwave background radiation has spots in it. So pretty soon we got to go to Stockholm, but only after getting lots of practice giving talks like this. The Swedes knew perfectly well that not all scientists can give public talks. So they had us come down and rehearse and give talks at the embassy in Washington. So we did. Anyway, I showed my chart a lot. And eventually I got to go meet the King of Sweden, and there he is giving me my diploma. And later on, I received a nice little golden medal, which is in a safe deposit box now. But there's a bronze copy over there in the lobby of Building 8, and you can see it. So, and there's another bronze copy that's down in the Air and Space Museum, and has been sent into space on the space shuttle and come back to be kept as a treasured artifact. Anyway, there I am getting my Nobel Prize. Of course, how do I feel? Well, the first thing I think is I'm in front of 2,000 people. I better not trip. I better not forget what to do. I'm nervous about my job in front of all these people, but it was okay. So what else about the Stockholm trip? Well, it's the biggest set of parties I've ever imagined. You don't just go get the prize, you get to go to parties and give speeches for 10 days. And so people are always amazed at this idea. I ended up, there were student parties. I got to be inducted into the Order of the Ever-Smiling and Jumping Green Frog. There was a dance with the students. On the very last day we were there, a choir came to our hotel room and sang songs, and the lead singer had a crown with candles on her head. And so this is something that the Swedes like to do, is lots of singing. There's an amazing story about this particular part of the ceremony, because Isaac Bashevis Singer got the Nobel Prize one year, and they surprised him in his hotel room. And he said afterwards, I don't know if you should believe this, but he said he was terrified because he thought not only had he gone to heaven, but it was Christian. So anyway, I think you shouldn't believe him, but it was a great story. Others interesting stories happen about that event too. So just to wrap up here, I love a little cartoon once in a while. Here's one from the New Yorker. Scientists confirmed that everything we know about the structure of the universe is wrongly wrong, and that's what I love about science. We find surprises all the time. And I tell this partly because I think so many of the public believe that science is about knowing a lot of things, a big box of facts. But actually what we're up to is trying to overturn the old facts and get new ones. And it's a sense of discovery, of participating in a huge worldwide process to discover the secrets of the universe. So I'd like to challenge people also with thinking about the interpretation. So here's a little excerpt from the Declaration of Independence. It says there, the laws of nature and of nature's God. Then it says, we hold these truths to be self-evident, that all men are created equal, that they are endowed by their Creator with certain unalienable rights, that among these are life, liberty, and the pursuit of happiness. So I think what we're working on is still a vitally essential question. I cannot really explain the answer to his question, but I think science is working on the parts. And now we, as a world, also have the job of interpreting the fact that all men are created equal and all people are created equal. We've changed the meaning of the word a little bit since people wrote that document, but I'm glad we have. So if I were to write a book now, it would be titled, We Have to Go Measure. That's my perspective, but I did already write one book, and this is it. It's called The Very First Light. It was written with John Boslow, a brilliant science writer, and you can find out all about what we've done in various places. There's the website for the Webb Telescope. There's the archive for cosmic microwave background radiation. You can read about all of the Nobel Prizes at nobelprize.org, and all of us have put in our autobiographical statements. And so there's everything you could possibly want to know about sharing the Nobel Prize. So let me wrap up here and be happy to have questions from you all. I think personally it's more interesting to talk about what we do rather than what I did. So thank you.
Thank you so much, John, for that beautiful talk. And to ask a question for John, please use the chat box to the right of the video player. If you don't see the chat box, try opening the event in a different browser. Okay, starting off. So what was your first thought when you won, John, as like when you really were able to sit with the fact that you won the Nobel Prize?
Yeah, well, first thought was, got a new set of responsibilities here. Don't mess up. All of your bad habits will be discovered. All of your mistakes will be uncovered. And now you are speaking for the team in a way that you never had to speak before. So use your opportunity well. Pay attention. That was a sense of great responsibility.
And what is it about your personal story, if there's one thing that someone would take away from your presentation today that you really want them to know?
Personal story. Well, I'd say it is that you have no idea how far you can go until you try. And so you might as well try. When we looked at the idea of proposing that satellite, I thought, well, it's very unlikely that we'll be chosen, but we should try. When we got to the idea of building the James Webb Space Telescope, everybody laughed at us because it was too hard. But I thought, yes, but we should try. And now it's almost done. So I'd say do not be too discouraged by the fact that something is difficult. That just means it's important.
I like that answer. Thank you, John. We have a question from Ansley in the chat. She says she's curious what Dr. Mather's favorite story from his career is to share.
Oh my goodness, favorite story. There's so many interesting spots. Well, right now I'm thinking of the fact that one day I came in to the office and my friends that had just been taking the first data from the COBE satellite said, we got it. Here's the first interferogram. And we're going to be able to make the science that we said we wanted. So they all printed it out and signed it. So I have an autographed interferogram from that first moment. That was a pretty big deal.
That's awesome. Wade has the question too. He says, what advice would you have for the science communicators who are watching? We have good intentions, we have strategies, we have plans, but from your point of view, how can we help scientists share the results of their work with the public?
Oh my goodness. Well, two things. Number one, practice. And number two, start at the beginning with people. A scientist almost never appreciates what the public perspective is on something. So we can learn a lot by practicing and by seeing who responds to what ideas. So over time, I've given up on trying to show a lot of things that don't work. People can't understand them right away, and try to put in stuff they do. So I've taken science communications workshops, and it's remarkable how scientists are taught to speak concisely and precisely about detailed concepts, but that's forgetting that the public has no idea what the words mean. So it comes home to me when I try to listen to other scientists talk about their work. Yeah, I say, that's hopeless. Are you not talking to me? So when I hear that from other scientists, I'm reminded that we just really have to step back and see what does the public know and start from there.
We have another question from Jean. He says, in your opinion, what is the next big thing from NASA in this decade?
Oh my golly, well, we have stuff going on in every area of science as well as in human travel. So I guess everyone knows we're going back to the moon. It's not impossible. It's hard, but it's not impossible. So I think we're going to do that. In late this year, in October, we're planning to launch the Webb Telescope, which will be an immense jump in capability for astronomers. We're always building more stuff to observe the Earth and figure out what's happening to climate and everything that we're doing on the Earth to understand what we should do to help the Earth survive its current changes. Learning about the sun, learning about the other planets in the solar system, and from the Webb Telescope, we might even discover that there are little planets that really are a lot like Earth. We're taking the next step. People want to know, are we alone? And I think the answer is yes, but they're really far away, these neighbors, because planets the right size and temperature to be Earth are common, but actually being Earth is probably rare, I think.
Another question came in from David. He wants to know, he says there's a lot of excitement about the James Webb Space Telescope, and how do you communicate the public importance of this observatory, and what are you most excited about it discovering?
Okay. I think number one, I want to know our history. So we built the observatory to learn something about all of the steps that happened from the first stars and galaxies to now. So of course you can't see your own history because the history has been sort of erased. But you can look at distant objects as you look back in time. So you see them as they were when they were younger. So you can see stars being born soon after the Big Bang. You can see galaxies grow. You can see black holes grow. You can see stars forming nearby. You can see planets growing around other stars. So we're going to be trying all of these kinds of observations. And so really, that's what we're going to look at. What we're going to see, that's still going to be a bit of a surprise. So we have just chosen what we're going to look at for the first year of Webb Telescope operations. I'm kind of hoping that there's something that we didn't guess, that there's something really missed in the idea of the early universe. I think it's not impossible, because all of the time we're finding something that we don't understand. In the area of planets, exoplanets around other stars, everything we know has been a surprise. So I think that'll still be true. We will find something that we did not expect.
What career advice do you have for anyone working at NASA and telling their own stories or communicating about their science?
Oh, do it. Um, uh, Two reasons. One is it's fun, and one is it's good for your professional career. If you can understand how to explain your science to the general public, then you can explain how to explain it. Sorry, then you can explain it in your proposals that you have to write. So somebody else will give you money for your idea. So I think really important to do it for two reasons. One, for fun, and one for success.
That's wonderful. So now you've traveled all over the world for your talks, thanks to the opportunities that you've been given. What do you think has been the most impressive place that you've visited, and what did you learn from that place?
I felt moved when I went to Padua, and I spoke in the hall where Galileo spoke, when he revealed his discoveries about the little stars around, as he called them, orbiting around Jupiter. So, oh my golly. So he was my hero for all these years, and to stand in the place where he stood, in the building where he stood, and to imagine what it was like to be him, well, that was pretty spooky. I liked it.
That's got to be so wild. We have another question that came in from Pram. They ask, any tips on communicating science to children? My 12-year-old wants to know what there was before the Big Bang and what the universe is expanding into.
Oh, well, number one, start with where the kids are, and don't try to give them all the answer all at once, because it's a conversation, not a lecture, right? So 12-year-old kid is already far enough along to have good questions. And so I see that. So what was there before the Big Bang? There's two kinds of answers. One is the simple one, we don't know. And the other one is the logical one, which is people say, well, what was the Big Bang? It was the time before there was time. So St. Augustine even worked this one out hundreds of years ago, that it's meaningless to ask what is there before time. So you can tackle that particular aspect two ways. Another thing you can say is, well, we're working on it, but that's not all that satisfying. And what is the universe expanding into? It's expanding into itself. People ask this question always because they have been given this idea of the Big Bang, which they picture as a little firecracker. And that's not the right picture. So try to explain what a universe expanding into itself would be like.
Another question came in. What is one of the proudest career accomplishments of yours that few people know about?
Oh, golly. Well, there are different kinds of career accomplishments. One is that I really feel proud to be working with the team that I work with. So they do the great things and I get to explain them. So that's one way of putting it. Then the other one is really things that I did all by myself. So a couple of things that stand out was I learned calculus from a book when I was in high school. And people think that's hard, but I just learned it from a book because we did not have advanced placement courses. So a lesson that I got from that was, well, if you really want to do something, try it. And don't be held back by the fact that there's no teacher. There's a way.
That's wild. I can't believe you taught yourself calculus. Who are some of the greatest storytellers that you enjoy listening to and that you've learned from?
Oh, well, let me start by giving credit to Alan Alda, who is a great storyteller, ranging from being on MASH to being a coach now for scientific storytellers. I took his course. NASA arranged for us to have a version of his science communications workshops. So I thought they were fabulous. They include what they call theater games, where you try to imagine being somebody else. That's really helpful. put yourself in the shoes of somebody else for any purpose, much less not just communication. Yeah. So yes, he's a great storyteller. Yeah.
Excellent. And how would you say that you've grown through telling your story?
Well, it's interesting to think about me because I'm not really very interested in me. I'm interested in the story and of the scientific discoveries. So I don't know. It's hard to answer that question. But I've been given so many opportunities to tell the story that every time I tell it, I feel proud, and that feels good.
One other question that came in from Vicky: what do you think is a better name than the Big Bang?
Well, technically speaking, I would say the expanding universe. But when Sky and Telescope had a contest to rename the Big Bang, they did not choose a winner. On the other hand, Calvin and Hobbes wrote a cartoon, and Calvin said, "Horrendous space kablooey." I think that's actually not technically correct either, but at any rate, I like that name, but it is not going to stick. So expanding universe.
Okay, we have a couple minutes left. I think we have 2 more questions in the chat. What's the most exciting part about working at Goddard for you?
Oh, I think whenever I have an idea, there's somebody to talk with who can make something happen. So a couple of years ago, I was thinking, gee, it would be great if we had an orbiting star shade to be able to look at other planets orbiting other stars. And so I mentioned this anyway, suddenly somebody turned up, and I'm working with him now. And so we're now working on the next steps towards seeing other planets. That's Eliade Peretz, by the way, to give direct credit. So, have an idea, somebody can turn up and make it happen.
Super cool. And our last question in the chat is, with all the wonderful discoveries, do you think we are still just scratching the surface of the universe?
Oh, yes, I definitely think that. We are only beginning to touch what we could possibly know. We're only beginning to touch what we could possibly build. And so I think it's not impossible, from anything I know, that we could build robotic intelligence, so that a very patient robot could travel to another star. But it would have to be an extremely patient robot, because even the best hints we have from physics do not give us a way to travel to Alpha Centauri in less than maybe 50,000 years or something. So it's a long trip. So on the other hand, there are always possibilities that we'll find something new. So there's that possibility. That's kind of a dangerous possibility of all that intelligence. I think we are on the cusp of learning how to manage our planet so it doesn't burn up. So I don't know whether government is going to do anything about it, but private industry is already. So when you say, what do I need? I need a zero carbon consumption system. Well, if zero carbon is cheaper, we'll switch to it. So it's getting there. So scientists and engineers make that happen. So I think that's one of the most exciting current developments, that people used to say, well, you just can't possibly do this. And now we're saying, well, yes, we can. We have a way. We can do good engineering.
And one more question for me, just because I'm curious. Why did you donate all of your money to education?
Well, I like to give back as much as I can.
Nobel Prize for everyone who's just tuning in.
Yeah, so I thought, well, number one, I want to be able to give back. This does not feel like my money. This feels like our money. This was a team project that built the COBE satellite, and so how can I give back? So one of my favorite summer intern projects is we give travel scholarships to a handful of really sharp summer interns based on what they're doing at Goddard. And I think, well, a lot of them will want to come back. Some of them have. So that's sort of one way for me to invest in our future together.
Well, thank you so much. Thank you so much, John, and to everyone who tuned in to his talk. It was really amazing, and we're just so grateful for the privilege of your time. So thanks again to everyone who listened, and if you need to check this out later on, you can look back and check it out in closed captioning too if needed. So take care and have a good rest of your day. Thanks,
Thank you, Laura.